Okay, so we got a pretty cool solution to a pretty conceptual based problem. Let's dive in. The statement reads, a magnetic dipole M equals negative M naught Z hat is situated at the origin in an otherwise uniform magnetic field B, given by B naught Z hat. Show that there exists a spherical surface centered at the origin through which no magnetic field lines pass. Find the radius of the sphere and sketch the field lines inside and out. Here we go. So if we were to use superposition, we could find the total magnetic field. The field at the center minus the field outside. Okay? Because in the dipole, we assume that the currents will be flowing back to or the field lines will flow back to one another versus the field lines outside. Alright, so anyways, we have the field given by the uniformity, which is B naught Z hat minus the field of the dipole. Okay, therefore, if we're looking at the origin, so we want it with respect to the R vector. So we take the dot product with R, and we see that we get some cancellations here. Z dot R hat is this cosine theta, typical expression there. R dot R is 1, and theta dot R is 0, so we get a cancellation of sign, and we have two expressions with cosine. Factor that out. Okay. The next part is a bit of mathematics. But we know that this thing is always equal to 0 for all theta, only when the coefficients on the cosine are equal to 0, and that happens at the surface R equals big R. So substitute in big R, and we see that B naught is equal to mu naught M naught divided by 2 pi R cubed. Now we can solve this to show what R is, and we get R equals mu naught M naught over 2 pi B naught to the 1/3 power. Pretty quick mathematics there. And we see that evidently no field lines cross the sphere. So let's plot it out. We see that we have a uniform field going up the page. We have this dipole at the center, which is running closed loops, as you might imagine. But then you see that we get some kind of repulsion there, and there is a sphere of radius R that the fields don't intersect at. That's pretty darn cool.